Block diagram reduction technique. Any physical system, if you look at, have different blocks, and those blocks are connected very complex fashion. So to find overall transfer function of the system, block diagram reduction technique is very useful. To illustrate that, let us take this example. Now this is example of a physical system block diagram representation. In this representation there are many blocks connected. Now all the blocks, if you look at, we have G1, G2, H1, and we have H3, of course G4, G3 and G5, and the final back is H2. So these blocks are connected either loop or forward path or in different fashion. Now the ultimate aim is to find the overall transfer function of the system using block diagram reduction rules. Now, so in any block diagram reduction problem, the main idea is try to reduce the blocks inside to outside, which means look at the inside reduction and try to reduce them one by one and come back to the outside. Now again, the another idea is try to eliminate summing points. In this particular problem, we have 4 summing points. So these 4 summing points must be eliminated using the rules which are available, and finally we can obtain the overall transfer function. So if you look at here, all the rules when you apply, they must be in their standard form. You cannot simply apply the rule when G1, G2 are connected in series or parallel. It should be according to the rule that is available. So in this block diagram, if you look at G3 and G4, these two are connected in parallel. Now, and they are in a very standard format. So no other connection is available for G3 and G4. So, and summing point we have plus. Therefore G3, G4 and the summing point can be minimized into a single block. And whenever the blocks are connected in parallel, simply we add or subtract depending upon the signs available. Therefore we are going to add them. That becomes G3 plus G4. Whatever the remaining block diagram is as it is. We are not going to change it. Only change is occurring only in the parallel blocks, and the resultant is G3 plus G4. Now again look at the block diagram. If you look at the block diagram, the other side of it, here I have G1, G2 which are in cascaded, therefore they can be multiplied. A resultant will be G1, G2, and we have feedback H1. So G1, G2 is like G and H1 is like H, and whenever you have negative feedback, it is G by 1 plus GH. So if you use that rule, then I will get one block transfer function by eliminating G1, G2 block, H1 block and summing point. Then coming to the other side of it. So the other side of it, I have a takeoff point before G5. Now I want to move the takeoff point after the G5. So when you move the takeoff point after the G5, then for this particular takeoff point you will get H2 by G5, because we introduce 1 by G5. So that becomes H2 by G5. What about the remaining blocks are as it is. So we already got this block is G1, G2 plus 1 plus G1, G2, H1, and this block is G3 plus G4, and again I have cascaded G5. I can simplify that into G3 plus G4 into G5, and I have one feedback like this, and finally I have another feedback. So first we'll try to eliminate the middle summing point which has got the negative feedback. Again the formula is same, G by 1 plus GH. So if we use that, then I can get one block here by eliminating the summing point. Now this block on this block will be in cascaded form. You can simply multiply, and again there is a feedback, final feedback, but the feedback is positive feedback. Whenever you have positive feedback, you have to use G by 1 minus GH formula, where G is the complete the forward path transfer function and H is your H2 by G phi. If you use the formula, you will get a big equation which is nothing but my transfer function G1 G2 G phi into G3 plus G4 divided by 1 plus G1 G2 H1 into 1 plus again it is G3 plus G4 into G phi H3. So this is my overall transfer function of the system. And once you have this transfer function, then you can do your analysis and you can do any kind of design for the system.